Alrighty, hello everyone. So today we're going to be doing another optimization problem. Woohoo! I actually think optimization problems are rather fun, but that is up to debate for a lot of people, and that's okay. So the problem reads as follows. A rectangular storage container with an open top is said to have a volume of 10 meters squared. The length of the base is twice its width, and material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. So we need to find the cost of materials for the cheapest such container. Cheapest is telling us minimization. But that doesn't really make a difference until the very end when we have to double check things. The first piece of information is that it has an open top. So it looks something like this. Keep in mind, I am not an artist. There are some people that are phenomenal at art and math. I am not one of those. Anyways, an open top. It's said to have a volume. So volume is equal to width times height times length, and it's going to be equal to 10 meters cubed. We have that the length of the base is twice its width. So they're giving us the cost for the material of the sides and the base, and we need to find the cost of the materials. So in order to find the cost of the materials, we have to find the area of the base, and we have to find the area of the sides. So the base is going to be, we have just one base, right? Since we have no top. I could make a joke with that, but this is a math page, so I won't. So we have the base, and that's going to be width times length. And the area of the sides, we have these sides, which is height times length over here. So 2HL plus the 2 back here. 2HW. The overall cost is going to be equal to 10 times the area of the base plus 6 times the area of the sides. Makes sense so far? We're just finding the cost of those sides. Okay, so we can go ahead and substitute in our two equations. So we have that cost is equal to 10 times WL plus 6 2HL plus 2HW. I'm going to go ahead and simplify this out. This gives me 10WL plus distribute 12HL plus 12HW. Okay. Notice that we have a lot of variables running around, which is not what we want. We want to be able to take the derivative with respect to one variable. So what we need to do is use some substitution. That's what all these good old pieces of information are good for. First, we want to substitute every L with a 2W. So we have W dot 2W plus 12H 2W plus 12HW. That's going to go ahead and give me 20W squared plus 24HW plus 12HW. We still have an H, we still have a W. That is not what we want. So we're going to go back to our piece of information, specifically the volume. If we know that W times H times L is equal to 10, we can also say that 2W squared times H is equal to 10. That's just from plugging this piece of information into here, and then we simplify. Now, what we have to do is divide both sides by 2W squared. So we have H is equal to 10 over 2W squared, or H is equal to 5 over W squared. So this is the little piece of gold nugget information that we're now going to sub in down here. So now we're going to have equals 20W squared plus 24, 5 over W squared times W plus 12, 5 over W squared times W. We're going to take this and put it onto a new page just so we have plenty of room to work with. God bless GoodNotes. I believe that's what this app is called. It's just really helpful when writing stuff down. All right, so now we have 20W squared plus 24 times 5. That gives us 120. We can cancel out a W, and that'll give us 120 over W plus 60 over W. Because we did the exact same thing, cancel one out, cancels out. What can we do? We can combine these two. So ultimately, we're going to get our cost equation just in terms of one variable. All of this so far, I hate to tell you, has just been algebra. Now we get into the fun little calculus part. We're going to start by taking our derivative. So we get cost is equal to 40W plus, and let me actually rewrite this problem using our exponent rules, plus 120W. So for this, I just used my exponent rules. And then we get plus negative 180W to the negative 2. I'm going to rewrite this as 40W minus 180 over W squared. And we're going to set it equal to 0. We're going to use some more algebra. We're going to move this to the other side by adding it. So we get 180W squared is equal to 40W. Next thing we're going to do, we're going to multiply so that we get everything on one side. 180 equals 40W cubed. Divide both sides by 40. That's going to go ahead and give us 9 over 2. So we just simplified 180 over 40 is equal to W cubed. Take our cube root, and we have that W is equal to the cubed root of 9 over 2. All right, let's look back at the question. It asks for the cost of the materials. So we have to go back to our cost equation, which is right here, and figure out whether this is a minimum. First things first, to figure out whether it's a minimum, we have to do a good old sign chart. So this is the cube root of 9 over 2. In our sign chart, we plug into our derivative. So we're going to be plugging into this part. Oops, this part. They're technically the same thing, but I don't want the one where it's equal to 0. If we plug in 0 into this, we can see that we would end up with an undefined number, just because of if we plug 0 into this, it'll be undefined. So we're going to pick any random number that is smaller than the cube root of 9 over 2. I believe that the cube root of 9 over 2 is bigger than 1, so I'm just going to go ahead and plug in 1. And the cube root of 9 over 2 is somewhat, what's 9 divided by 2, guys? 4.5. So the cube root of 4.5 is definitely going to be smaller than the cube root of 27. So I'm just going to go ahead and say that's about 10. Doesn't really matter what numbers we're plugging in. We just want to double check that it's a minimum. So if we plug in 1, you're going to see that if we notice our signs, 180 over 1 squared is going to be much bigger than this. So it's going to give us a negative, which means that it's going down. And when we plug in 10 squared is going to give us 100. We have the negative 180 over 100. Well, now in this case, 180 divided by 100 is like 1.8 versus 400 is going to be much bigger than that. So it's going to be positive. So double checked, it works. This is a minima. Yay. Because now that we know it's a minima, we only have to plug it into our cost equation. So our ultimate cost is going to be 20 times the cube root of 9/2 squared plus 180 over the cubed root of 9/2. And that is our final answer. A little messy, but that is your proper exact answer. Anything after this with Desmos would be a decimal equivalent, which feel free to do if your class lets you do that. I just know on the AP exam and certain exams, you have to be leaving it in an exact answer. But that is our cost. All right, thanks for watching.